Dear children, today we will derive the relationship between radius of curvature of a spherical mirror and its focal length. You know what is radius of curvature of a spherical mirror and what is focal length. So before to derive the relation, first we have to know what is the convention. So in mirror and the lens, we will use Cartesian convention. So what is Cartesian convention? You know, it is x-axis and it is y-axis. It is origin, right of the origin, that is positive, left of the origin, that is negative, above origin, that is positive, and below origin, that is negative. So in case of mirror, it is a convex mirror. You place a convex mirror such that the reflecting side is left, is towards left. So in mirror, all the measurements are measured from the pole. So you just imagine here pole as the origin. So left measurements are negative, right measurements are positive, above measurement, the measurements above the pole or above the principal axis, that is positive, and below the principal axis, that is negative. Suppose, for example, you place object at here. So what will be the object distance? Object distance will be, you see, it is left of the pole. So object distance will be negative. If image is formed at the right side, then image distance will be positive. If image is formed on the left side, then image distance will be negative. So you know, simply to solve numericals in case of mirror or in the lens, you will learn you use the Cartesian convention. Right measurement, that is positive, left measurement, that is negative, above the principal axis, that is positive, below the principal axis, that is negative, and all the measurements are from the pole of the mirror. So now here we have drawn it is the concave mirror and it is the convex mirror, and here we have assumed the mirrors of small aperture. What is aperture? It is the, suppose it is a concave mirror and it is just two-dimensional point of view. From three-dimensional point of view, but the mirror like this. You imagine it is the part of a sphere. So what is this boundary? Boundary will be the circle. The diameter of the circular boundary of the spherical mirror is called as aperture. That means it is the aperture. If it is A, it is B, then AP is the linear aperture. So here we have assumed, here it is concave mirror and here it is convex mirror of small apertures. So let us come to the figure. You see, it is the principal axis and it is the pole, and you see the incident ray FB parallel to the principal axis. After reflection, it goes along BD, and you know, if the incident ray is parallel to the principal axis, the reflected ray meet the principal axis at the focus. In case of concave mirror, it is the center of curvature. It is the part. This mirror is the part of imaginary sphere. So BC will be radius, and you know, always the radius is normal to the surface of the sphere. So BC is normal to this mirror at this point. So now you can consider BC as the normal. And what is the angle of incidence? It is the incident ray. It is the normal. The angle between incident ray and the normal is angle of incidence, that is I. It is the reflected ray. It is the normal. The angle made by the reflected ray with the normal is the angle of reflection. Similarly, here you see it is the incident ray. After reflection, it goes along this path. You know the concave mirror is converging mirror. So after reflection, this ray meet the principal axis at this point. Actually meet. But here you see it is the convex mirror. It is diverging mirror. So the parallel incident ray means incident ray parallel to the principal axis. After reflection, it will diverge from the principal axis. When it is produced backward, it appears to diverge from the focus. It is the point of the principal axis that is called as focus. It is the definition of the focus. Similarly, it is the center of curvature. You join BC, and definitely BC as discussed. It is the radius, and it will be normal to this convex mirror at this point. So it is the incident ray, it is the normal. So angle made by the incident ray with the normal is the angle of incidence. Similarly, this angle made by the reflected ray with the normal is the angle of reflection. So now you come to this figure. As these two lines are parallel and it is the intersecting line, so this angle is equal to this angle because they are alternate angles. So you can write I at here. As I is equal to R, it is the law of reflection. So in triangle BCF, this angle BCF angle is equal to CBF angle as I is equal to R. You know, in a triangle, if two angles are equal, their front sides are equal. So you see, it is I, what is the front side? That is BF. It is R, what is the front side? That is CF. Therefore, BF is equal to CF. Let it be equation number 1. So now come to, as we have taken the aperture is small. This aperture is small. That means B is very close to P. When B is very close to P, then BF is almost equal to PF. For small aperture, BF is nearly equal to PF because B is very close to P. Equation number 2. So now compare equation 1 and equation 2. You will get from equations 1 and 2. You can write PF is equal to CF. Let it be equation number 3. Now PC. PC you can write PF plus CF. But here we find CF is equal to PF. That equal to, in place of CF, you can write PF. That is 2PF. So now you use the convention. What is PC? PC is the center of curvature, it is the pole. PC is the radius of curvature. So for this concave mirror, what is the sign of the radius of curvature? Just told the Cartesian convention, it is the left measurement. So left measurement means it is negative. So PC is minus R for this mirror. And what is PF? You see, F is the focus. So PF is the focal length. So it is the left measurement. So it is negative, minus F. So you remember, in case of concave mirror, the focal length is negative because focus comes in the left side of the pole. So BF is, or focal length is negative in case of concave mirror. So now you use these values in equation 4. So from equation 4, that is in place of PC you write minus r and it is minus 2f, or you will get r is equal to 2f. So here this relation we have derived for the concave mirror. Then for convex mirror, you see all the writings are same. You see, now we can verify. We have already told this is angle of incidence, it is angle of reflection. So you see, it is r, so it will be r because these two angles are vertical opposite. You see, it is same line, it is same line. So this angle is equal to this angle, that is r. And you see, these two lines are parallel. It is an intersecting line. So this angle is equal to this angle because they are corresponding angles. So now come to this triangle BCF, that is I is equal to r. That means you see BCF angle is equal to CBF angle. So BF is equal to CF. The front sides are equal. But aperture is very small. We have taken, so B is very close to P. That means BF you can write it as PF. Similarly, from equation 1 and 2, PF is equal to CF. So what is PC? PC is PF plus CF, and CF is equal to PF. So in place of CF you can write PF. So it is 2PF. Now you use the convention. It is right measurement because center of curvature is right of the mirror. So the measurements are positive. So here PC is plus R. And what is PF? Here you see focus is right of the mirror. So focal length PF is the focal length, that is positive. So you remember for convex mirror the focal length is positive. So now R is equal to 2 plus R is equal to plus 12, that means R is equal to 2f. So the same relation we got, R is equal to 2f means radius of curvature is twice of the focal length, both for concave mirror and for convex mirror. Also this relation is valid for plane mirror because you can consider the plane mirror as a spherical mirror. Then how? Because if you take a large sphere, a small part of a large sphere, that is nearly a plane. So you can assume plane mirror is a spherical mirror whose radius of curvature is very large, that is infinite. So here you can remember that radius of curvature of plane mirror is infinity. Radius of curvature of plane mirror, that is infinity for plane mirror. If radius of curvature is infinity, then what is focal length? Focal length is r by 2, that is infinity. So we have derived the relation between the radius of curvature and focal length. In the next class we will derive the mirror